Dear student, in this video, I am going to discuss about the diffusion-limited and flow-limited diffusion across alveolo-capillary membrane and DLCO. So what is the learning objective? At the end of this session, you will be able to define diffusing capacity. You will be able to explain the concept of flow or perfusion limited and diffusion limited diffusion. Why diffusing capacity for carbon monoxide or DLCO is measured as an index of diffusing capacity and diffusion capacity of oxygen and carbon dioxide. Now, gases diffuse from alveoli to blood in the pulmonary capillaries or vice versa across a very thin alveolo-capillary membrane, which is made up of pulmonary epithelium and vascular endothelium or capillary endothelium and their fused basement membranes in between. Here you can see the alveolar epithelial cell consisting of pneumocyte type 1, type 2 and the capillary endothelial cell. In between you have the basement membrane. Now, as per Fick's law, the rate of diffusion across this membrane, it will depend upon few factors. So, V gas, the relationship is V gas is equal to AD into P1 minus P2 divided by T, where V gas is the volume of gas diffusing through the tissue barrier per time, that is the rate of diffusion, where A is the surface area available for diffusion, T is the thickness of the barrier, P1 minus P2 is the partial pressure difference of a gas, and D is the diffusion coefficient of the gas or diffusivity. Now, diffusion constant or diffusion coefficient, it is determined by Henry's laws and Graham's law. We will see it later. So, what is the clinical application of this Fick's law? From this previous slide, we can see that the rate of diffusion is directly proportional to the surface area and the pressure gradient, and it is inversely proportional to the thickness of the membrane. So, if the surface area it is decreased, that means that will reduce the rate of diffusion as it is directly proportional. So, in which condition it can be decreased? It can decrease in alveolar collapse or alveolar fluid. Second point, the pressure gradient is also directly proportional to the diffusion rate. So, by any means, if the P1 minus P2 it is reduced, then there will be less diffusion. For example, in high altitude or alveolar hypoventilation, diffusion will be less. Third factor is the thickness. Thickness is inversely proportional. So, if thickness is increased, there will be less diffusion. So, increased alveolar tissue thickness caused by alveolar fibrosis or alveolar edema, that will reduce the movement of oxygen across alveolo-capillary membrane. Diffusion coefficient will be dealt differently, that we'll discuss later. Now, under normal resting circumstances, a red blood cell spends about 0.75 seconds in the pulmonary capillary. And if you see that this red blood cell in this time 0.75 second, the oxygen equilibrium it comes at 0.25 seconds. So within 0.25 second, adequate amount of oxygen will be taken up by a single RBC. Okay, so remaining 0.5 second it acts as a safety factor, because when we do exercise the rate of flow will increase, so that will decrease the transit time. If the transit time is decreased 0.75 second to say 0.25, then also the oxygen acquirement from the alveoli will be adequate. So this is the 0.75 second is the time at the resting state. So in the exercise, when the rate of flow is increased, the transit time it may be reduced to 0.25, and that is in that reduced time also adequate oxygen can be taken up by the RBC. Now come to the flow limited diffusion. This diffusion across the membrane, it can be flow limited or perfusion limited. The best example of flow limited diffusion is the N2O, that is an anesthetic nitrous oxide gas. You can see here nitrous oxide is coming, is high partial pressure in the alveoli. So there is a P1 minus P2 gap is high, so it is readily entering into the capillary. But the point is, when it will enter into the capillary, alveolar capillary, hemoglobin does not bind with the N2O. So the free N2O level will be there, it will not form a bound component, and it will reach to an equilibrium or saturation almost immediately after the blood enters the capillary. From here you can see that along the x-axis they have plotted the time, along the y-axis the partial pressure. We can see that it is not 0.25 second, it is only 0.1 second it has come to an equilibrium, that is all the nitrous oxide it has entered, it has been captured. So there is no P1 minus P2 gradient. Okay, so in this situation how can we increase the further diffusion of N2O? Already the saturation has been achieved. Saturation is achieved means no further diffusion is possible. So within this 0.75 second, if we want to resume the N2O diffusion further, increase the N2O diffusion further, what we need to do, we have to what we need to do, we have to put a fresh set of blood into the alveolar capillary. This fresh set of blood must enter into the capillary. So this set of blood which has already has been equilibrated, it has to be moved, and a new by the blood flow, by a fresh blood flow in the pulmonary artery capillaries, a fresh blood column must enter. So this fresh blood column will not have any N2O. So there will be a pressure gradient will again be situated, and it will help the diffusion process. So this we can say in this way, if we move the blood column, a new fresh blood comes and there will be further diffusion. Otherwise, diffusion will come to a stagnant point. So from it we can say that the nitrous N2O actually it is its diffusion is limited by the blood flow or the perfusion limited. Okay, so N2O taken up is not limited by diffusion but by amount of blood flowing through the pulmonary capillaries. So its diffusion is flow limited or perfusion limited. Now come to the other example, that is diffusion, which is diffusion limited. The best example is the carbon monoxide. Okay, carbon monoxide, when it will enter into the blood, it will be readily taken up by the hemoglobin. Okay, it will because there is a high affinity between the carbon monoxide and the RBC. So its partial pressure reaches only a fraction of partial pressure in the alveoli. So you can say that when it will enter, it will combine with the hemoglobin. Okay, so the free carbon monoxide is not available. So P1 minus P2, this gradient is maintained. It is constant. So flow will continue on and on and on. Okay, so on the other hand, we can say carbon monoxide is taken up by hemoglobin, and at such a high rate that partial pressure of carbon monoxide stays very low, and equilibrium is not reached in 0.75 second in the blood in the pulmonary capillaries. Therefore, the transfer of carbon monoxide is not limited by perfusion at rest. Instead, it is diffusion limited. Okay. So here we also see that P1 minus P2 is constant, and the transfer of carbon monoxide, it is diffusion limited. This property makes carbon monoxide an excellent gas for evaluating the lungs' ability to diffuse gases, and is used in what is called the diffusion capacity of carbon monoxide or DLCO test. So if we want to measure the diffusion capacity of the alveolo-capillary membrane, we will use this gas. This carbon monoxide will be used for this, because carbon monoxide transfer, it is diffusion limited. Now, what is the value of this diffusing capacity of carbon monoxide? That we can derive by the Fick's law. We know that rate of diffusion is equal to A into D divided by T into pressure gradient. A into D divided by T is taken as the diffusing capacity. So if we solve the equation, we can say the diffusion capacity DL is equal to flow divided by P1 minus P2. In case of carbon monoxide, this is 50 ml per minute divided by 2 millimeter of mercury, that is around 25 ml per minute per millimeter of mercury. So that is the diffusion capacity of lung for carbon monoxide monoxide, we take it as a standard value. Now from this picture we can see the two extreme conditions, N2O which is perfusion limited or flow limited diffusion, whereas carbon monoxide it never reaches the equilibrium, so it is the diffusion limited diffusion. Now where comes the oxygen and carbon dioxide? From this picture we can see that oxygen is intermediate between these two. Now diffusion capacity of oxygen and carbon dioxide. So here we can see that under normal condition, when oxygen it will come to the from alveoli to capillary, it will bind with the hemoglobin and it will reach its equilibrium value, say at around 0.25 seconds. Okay, so before it reaches the equilibrium value, then the diffusion of oxygen, it is diffusion limited. But once it has reached the equilibrium, so if I further want to increase the oxygen transfer or diffusion, then I have to remove the equilibrated blood and we need to have a new fresh blood here. So the later part, it is perfusion limited. So initial part of the oxygen, it is diffusion limited until and unless it reaches the saturation. Once the saturation is reached, its diffusion will be perfusion limited. Now what is the value of it? So value again we can calculate it by this fixed law, that is the first is the VO2, the rate of oxygen uptake by the lungs, ml per minute, divided by the pressure difference between the alveoli and artery of oxygen. Okay, the numerator represents how much oxygen is being taken up per minute, denominator is the driving pressure for oxygen diffusion. Now here if we can, the typical value if we take it, it is 250 divided by 100 minus 40. We know that alveolar partial pressure is 100 and alveolar arterial pressure in the venous valve is 40. So it is 250 by 60 at around 4.17 ml per minute per millimeter of mercury. But originally if we see the diffusing capacity of oxygen, it is not 4, it is 21 ml per minute per millimeter of mercury at rest. Okay, so why this difference is happening? Because this fixed law, it assumes a constant capillary pressure. Okay, in reality, oxygen does not diffuse across the entire capillary rate at the same length at the same rate. Fixed calculation uses an average capillary oxygen pressure of 40 millimeter of mercury. But as oxygen diffuses into the blood, the capillary partial pressure rises, reducing the pressure gradient. So the actual driving pressure is not constant, and the calculation underestimates the effective diffusion over time. Second point is hemoglobin binding is also not accounted for fully. Oxygen, it rapidly binds with the hemoglobin. It maintains a low free oxygen partial pressure in the blood. This maintains a steeper pressure gradient than assumed. So fixed law does not consider how hemoglobin acts like a sink for oxygen. So the real effective pressure gradient is greater. So more oxygen diffuses than the fixed equation suggests. So how can we get the actual value of diffusing capacity of oxygen? So clinically we will derive it by multiplying 1.23 with the DLCO. Okay, DLCO is taken as a standard. If we multiply it by 1.23, that will give us the value of diffusing capacity of oxygen. And that is 21 ml per minute per millimeter of mercury at rest. Now, what about the diffusing capacity of the carbon dioxide? It is 20 times greater than oxygen. It is 400 to 450 ml per minute per millimeter of mercury at rest. Why? Because we know that this diffusion, we know that from Fick's principle, we know the diffusion coefficient into the pressure gradient divided by the thickness. This was the law. But this diffusion coefficient, it is determined by the solubility of any gas, that is divided by square root of its molecular weight. From this we can say solubility of gases at body temperature, the oxygen has 0.025 solubility, it is less, whereas carbon dioxide has higher solubility, that is 0.592. So from it, it is clear that if we compare oxygen and carbon dioxide, you see that solubility of carbon dioxide, it is greater. So although it is a heavier gas, we know that lighter gas, so less molecular weight, should have more diffusion coefficient. Okay, but we can see that the molar mass of carbon dioxide, it is 44, whereas the molar mass of oxygen is 32. But as the solubility is much more higher, you can see here, solubility of carbon dioxide is 33 into 10 to the power minus 3, whereas in that case oxygen is 1.3 into 10 to the power minus 3. So as the solubility is higher, so carbon dioxide is diffuses much more readily than oxygen through the lipid layer because of its far more soluble, even though it's higher. Now, diffusing capacity of the lungs for carbon dioxide is much greater than the oxygen, and hence, what is the clinical importance? Carbon dioxide retention is rarely a problem in patients with alveolar fibrosis, where thickness is there increased, even when reduction of diffusing capacity of oxygen is severe, because its diffusing capacity is much more higher. So mild fibrosis cannot alter the carbon dioxide transport, but it can severely hamper the oxygen transport. So how have we have calculated the solubility? That is by the Henry's law. From here you can see the calculated value of oxygen, solubility of oxygen and the carbon dioxide. So from this, it is clear that uptake of various substances during 0.75 seconds, they are in transit through a pulmonary capillary, and N2O is not bound to the blood, so its partial pressure in blood rises rapidly to its partial pressure in the alveoli, so it comes to equilibrium very rapidly, whereas carbon monoxide is avidly taken up by the red blood cells, so its partial pressure always remains at a fraction in the alveoli, and oxygen is intermediate in between these two. Now, how oxygen can be either perfusion or diffusion limited, that I have already told you. When oxygen diffuses across the alveolar wall into the blood, and it enters into the RBC. Okay, until and unless it reaches the equilibrium or saturation, that initial part, the diffusion will be, it is diffusion limited. But once it will reach the equilibrium point, beyond this point, the transfer of oxygen is the perfusion limited. Okay, and perfusion limited diffusion of oxygen, it becomes significant when the patient has either decreased cardiac output or decreased hemoglobin, that is in anemia. If diffusion properties of the lungs are impaired, the partial pressure of oxygen in the capillary blood never equals with the partial pressure of oxygen in the alveolar gas during the normal alveolo-capillary transit time. So thus, under normal circumstances, the diffusion of oxygen, it is perfusion limited, but under certain abnormal perfusion pulmonary conditions, the transfer of oxygen may become diffusion limited also. Okay, so when the diffusion limited will happen, when the equilibrium will not reach. How it is possible? Because in certain conditions where the partial pressure will always remain a gap between them. Okay, and perfusion limited will become significant when the patient will have decreased cardiac output or decreased hemoglobin or anemia. So another important point, this transfer of oxygen, it is not same at low alveolar oxygen pressure. At low alveolar partial pressure of oxygen, you can see that it sets the upper limit for the end capillary blood for PO2. As the oxygen content of the arterial blood is decreased, the mixed venous PO2 is also depressed. The even greater decrease in alveolar partial pressure of oxygen causes a decreased alveolo-capillary partial pressure gradient, and the blood PO2 takes longer time to equilibrate with the alveolar PO2. So, in these persons at low alveolar oxygen concentration, the gradient will be maintained for a longer time. The equilibrium will be reached at a later time. Now, transfer of carbon dioxide, the time course of carbon dioxide transfers from the pulmonary capillary to the blood, the alveolus. In a normal person, Okay, the mixed venous partial pressure of carbon dioxide is 45 millimeter of mercury. In the alveolar partial pressure of carbon dioxide is 40 millimeter of mercury, and the equilibrium is reached at 0.25 of a second, about the same time for oxygen. But the diffusivity of carbon dioxide, it is about 20 times than the oxygen, but the partial pressure gradient is normally only about 5 millimeter of carbon dioxide, whereas it is about 60 millimeter of mercury for oxygen. So carbon dioxide transfer is therefore normally perfusion limited, although it may be diffusion limited in a person with an abnormal alveolo-capillary barrier. So this diffusion capacity is why it is required, because we can diagnose properly the obstructing and restrictive lung disease by measuring the value of DLCO. If we find the obstructive lung disease, to pinpoint the diagnosis whether what is the cause of this obstruction, if we look at the DLCO, if the DLCO value is low, then we can call it is due to emphysema. If the DLCO value is normal, then we will call the obstruction is due to chronic bronchitis or asthma. Similarly, in restrictive lung diseases, you see that if the DLCO value is low, the cause of restriction probably is the interstitial lung disease. But if it is normal, then chest wall disorders, neuromuscular disease, obesity may be the cause. Thank you.